Okay, so let's get started with the second section of probability. Today we're going to talk about conditional probability, and that is where you're not dealing with independent events. So far, in our last section on basic probability, we were dealing with independent events, something like rolling a dice, where every time you roll a dice, there's 6 options and 6 options only. Or we did some card drawing, but remember that in the wording of those questions, it said with replacement. In other words, we put the card back in the deck and then we drew from the exact same pool. Maybe if we had socks in a drawer and we picked out a sock and then we threw it back in and picked out another sock. I believe in your homework there were some questions, definitely in the very first one, that we're dealing with simple probability that occurs when there are no other steps going in consecutive order. So let's first start talking about one of the most important things, which is a complement probability. The notation for a complement probability is P with that little A there. Oh, hold on. Oh, wait, maybe I can do it this way. Okay, I found it. Yay! Okay, we win. So let me see, y'all. Sorry, it's been a long day. I'm just trying to teach today. Okay, so right here, this is the symbol for the complement. It is a bar. It's often called bar, so this would be a bar. It can also and will show up in later times as a little C above, and we'll be doing this kind of stuff in Unit 5. Okay, but this is what the definition is. So the complement of A, P A bar, is equal to 1 minus the probability of getting A. In other words, let's do an example here. And we're dealing with cards. And we want to know, what is the probability that we don't get an ace? That's what this says, that we do not get an ace. Okay? And that's going to be 1 minus the probability that we do get an ace. All right, and we know that is 1 minus, and we know that there are 4 aces out of the 52 cards. Okay, and so when we do the math here, we get 0.923. I'm going to want you to write your stuff in a sentence. So the probability of not getting an ace is, and remember, this is written as a probability. Let's write the percentage or something like that, is 92.3%. Okay, pretty good odds there. How about the probability of not getting a 4? Well, that's the same as the probability of not getting an ace, because there's the same number of aces in the deck as there are 4s. So this would be 1 minus the probability of a 4, which is equal to 1 minus 4 over 52, which would be the 0.923 as well. So the probability of not a 4 is 92.3%. And then over here, the probability of not being a face card. So that's going to be 1 minus the probability of getting a face card. And we worked with this last time, the face cards. There's 12 face cards in a deck of cards. So that's 1 minus 12 over 52, which gives us 0.769. So we could say 76.9% chance of not getting face card. Okay, I don't need the sentence to be great, but I need to make sure that it's very clear what you are saying there, right? Let's keep on going here. You'll notice some of the tables from the last lecture here. We're going to do a few other things with them. This table below summarizes the grades in gender and class. And the question asks, what is the probability that the student chosen did not earn a C? Well, first we need to write this down in probability language, right? So, and this has been awful thin. Let me go a little bit thicker on my point. Appreciate that. Okay, so we would say the probability of not C, right? So what it says, what's the probability that a student chosen did not earn a C? So probability of not C, that's going to equal 1 minus the probability that they did get a C. That's going to be 1 minus, and what is our probability that they got a C? Well, 65 is our total, and that is the number on the bottom, right? And we're looking for how many got a C, and here's the total of how many got a C. So we have 25 over 65, and when we do that math there, we get 0.615. So we could say that there is a 61.5% chance not a C. Okay. All right. So let me give you a you do here. We haven't done that, but I don't feel like I did a you do last time. So let's give you a you do here. I need you to definitely set up the equation, right? What we're looking for here. So it's the probability that a person chosen at random has at least one credit card. Now, the thing that becomes kind of difficult in probability questions is you have to read the question critically. Just like in our first unit of financial problems, you really had to read those questions critically to understand if that was a one deposit or many deposits or a payment or many payments. It required you to read carefully, and these questions are also going to require you to read carefully and a little bit with some critical thinking. So having at least one credit card, you need to think about how can we do this? We're not adding up more than one column, so having at least one, so at least one, that's the equivalent of the probability of not something. I'm going to give you a few seconds, about 30 seconds. So I really struggled with this when I first learned probability and statistics. I really, really struggled with being able to understand that at least one meant not zero. So we're looking for not zero. So that's 1 minus the probability of getting zero. I'll put a slash in it so it doesn't look like an O, and here it is, or 0. So that's 27 out of our total of 81. So this is going to be 1 minus 27 over 81. And that's going to give us 0.666666666. Keeps on going, right? Now, I don't want you to write it like that. That is equal to 0.6 bar, which is the neat way to write that, saying that that 6 repeats. But when we write our sentence here, it doesn't hurt to have it written like this. So then you see that it's 66.7 percent chance that they have at least one credit card. Okay. I hope that you followed that and saw that coming. I just really struggled with those kind of words when I was learning this. Okay, so I started this lecture today kind of explaining that last lecture we were dealing with what are considered independent events. This is independent events. This occurred in let's see, lecture K. Okay. In lecture K, we dealt with independent events, and that's like rolling dice or drawing a card, then replacing it, and drawing again. These are independents, and let me talk about this drawing of a card. Let's talk about that for a minute, right? So in the previous lectures, we had 52 cards, and I might have said, what's the probability of a face card? So let's see, let me just write this off here. So in lecture K, probability of a face card was equal to 12 over 52. Then I also ask you the probability of two face cards, right? I know I asked you that, but I also said with replacement, which meant I draw to see if I have a face card. So that is 12 over 52. And then I put that card back. So for lecture K, they're independent, and I put that card back. And you're only going to notice that in the wording of the question. Okay? One of the things we're going to start asking ourselves is this situation independent, meaning every time I draw something out of it, it is from the exact same pool as the first time I drew something out of it? In other words, do I replace it back in? Or what we'll be doing with the dependent in a second. But I'm sorry, let me get back to this because I fell off there. So the probability of two face cards with replacement, this is the first card. And then when we do the second card, the probability is exactly the same because there's still a possible 12 face cards to draw from the possible 52 cards. We didn't remove anything. We put it back in. It was replaced. This scenario is independent. It's not the way most probability works. What we're going to be talking about is dependent events. But let me point back to my PowerPoint because I got off and I quit paying attention to what I wrote here. So this information in these formulas that we got last lecture are all for independent events. Okay? This formula that says P of A and B is P times A times P of B, a probability of A times the probability of B. So the probability of A and B equals the probability of A and probability of B if independent. Okay? And the probability of A or B is equal to this business if independent. Now, we have the other side of the coin. We have dependent events. So as two or more events are considered dependent if the occurrence of one event affects all the additional subsequent events. In other words, if I want to know the probability of two face cards when it is dependent, meaning no replacement, when I draw the first card, there are 12 options out of 52 cards. When I draw the second card, it's not out of 52 anymore. It's out of 51 because we did not replace that card. Okay? So we didn't replace that card, and so then this would be most likely 12 out of 51, but I don't want to get in the weeds on that because that's really not a great example, but a pretty decent example. Okay. Now, it's important to note a few things. So let me just take a second, take a swig off my root beer. And let's talk about what's important to note here. Note this weird notation down here. Okay. That notation, P of B given A has occurred. That's what this says. This is what's the probability of B given, that's what this line is for, given that A has already occurred. That's what that notation says. And the way you read that notation is backwards. Notice I started with, well, the fact that A already occurs. It's not really backwards, but kind of is as we start going. I'll show you the way that we'll be reading it, but it is kind of A happened, then B happens. It's what's the probability of B after A has occurred. Now, another thing to note is the probability of A or B is not something that we're going to consider in this class. I'm not saying that it doesn't happen. We're not considering it in this class. Okay, remember the survey class, we're just looking at some broad topics. Okay. So the probability of A given B has occurred reads as the probability of A given B has already occurred. And it can be written like this. We can also do things with this formula, but we're not going to have to use very much with this formula because you're going to see here that you don't really need the formula to think through how to get the next thing. So let's take a look at this next example here. Now, two things are important here. First, for you to write the problem with the probability notation. And then second, of course, is to compute it, right? When you're done writing it all up. Okay. So let's read what this says. Find the probability that you will draw a red marble than a green marble. So we have a bag containing 5 green, 3 blue, and 2 red marbles. That's a total of 10 marbles, right? And that's going to be our denominator. For the first one. For the first parenthesis with the numbers in it, okay? So let's start off here. Let's write out what this is asking us to find. Find the probability you will draw a red, then a green. Now remember the way that this is written. It is written as the probability that this will happen given that already happened. Okay, so that's kind of the setup here. So we're going to write here, it's going to be the probability, and which one's going to come first. We want to know what's the probability you'll draw a red, then a green. So it is the probability that we will get green, given we have already gotten a red. So this is the setup in the probability notation. Now, it's to be noted that it's written backwards, right? So the thing that happened first comes second. This is what happened first. It comes second in the notation, all right? Now, when we compute this, we first go, what is the probability of red? Because that is first. And then times the probability of green given red. And so, what is the probability that you'll draw a red? Well, the probability of drawing a red is there's 2 marbles out of the total 10 marbles. That's our first draw. What is our second draw? Then we're looking at green. Now, how many marbles are left in the bag? There's only 9 marbles left in the bag, and this time we're choosing green. And how many green marbles are there? 5. Okay. So then we'll compute this here. When you do the math, let me get there, is 0.1 continuing, right? And so that means that 11.1% chance that you will draw a green after drawing a red. And if we were to say, what is the probability you draw red after drawing a green, that would give us a completely different situation, you know. So if I wanted to know the probability of red given green, let's see how that changes it just for giggles here. Probability of the red is our probability of the green, because remember we got to work it this way. Probability of the green is 5/10 times, so that's a green. And then the probability of the red is going to, the bottom is going to be 9 now, because there's only 9 marbles and there are 2 red marbles, and this would give us 10/90, which is 1/9, right? And let me get my calculator. That might be 0.1 again. I'm a little slow today. Yeah, that still gives you the same. But it won't always give you the same. Bad example. That must be why in the past I haven't done it both ways. I probably did it both ways one time with this example, and I was like, well, that didn't prove my point now, did it? So that didn't prove my point, but you can see that it would be different. See this, this is a 2 and a 10 in the first one, and it would be 5, 10 in the first one there, and then this was 5 over 9 in the second one, and this was 2 over 9 in the third. So because all the numbers on the top and all the numbers are on the bottom are exactly the same, and the commutative properties with multiplication, it makes sense, but it wasn't the point I was trying to make. Darn it. Okay, let me turn my attentions to the next one. Find the probability that you will draw a red, then a green, then a blue. So probability, and we're going to have 3 of them, and we need to choose the red one first, and then the green one, and then the blue one. Okay, remember that these guys start here, go this way. That's the order how that you have to compute it. That's the order in which you need to write it. So first, probability of red. There are 2 red marbles out of the 10 total marbles. The next one would be the green. There are 5 green marbles out of the last 9. Oh, sorry about that. I don't know why that did that. See if I can't make it work now. I don't know. 9. Okay, perfect. And then finally it asks for blue. There are 3 blue marbles, but now how many marbles are left in the bag? Only 8. And when we do that math there, it's 0.042. I want to encourage you to be very, very careful when you convert from a decimal to a percentage. You need to flip that decimal point over 2 spots to the right, no matter where that decimal point is, okay? And so this gives us 4.2% chance of drawing red, then green, then blue. Red, then green, then blue. All right, cool. Let's keep on going here. Okay. So let's take a look at our next example. All right, we're going back to the cards. I hope that you've gotten familiar with the card situation here. Remember that each specific value, there are 4 of those. There are 4 kings, there are 4 queens, there's 4 sevens, there's 4 threes, okay? There are half of the deck is black, half of the deck is red. So let's see, we could say 52 cards. So we got 26 black, 26 red. We have 13 hearts, 13 diamonds, 13 spades, and 13 clubs. And then each value, or each digit value, there is 1, or we'll call it ace, 2 through 10, jack, queen, king. I just felt like I needed to review all that real quick. Okay, so now that I've done that, let me leave you with a you-do here. You got to get your hands in it. You got to get your hands a little bit dirty. You got to be brave enough to fail and do it wrong and brave enough to try it while we're doing it. I'm going to set up the very first one here, and then I'm going to give a few minutes for you guys to work it through. As always, if I come back and start working it before you're done, just pause the video and finish the problems, okay? So the first one is you draw a king and then an ace. Now remember, we've got to write them kind of in this order. So the probability that you get an ace given you've drawn a king here, right? So you draw a king and then an ace. So we got to write it backwards. Ace is going to come first. Maybe my little thing here might be a little confusing. That's just the way I see it. I'm not gonna, maybe I'll just erase it. I don't know. I'm second thinking myself. I'm super tired. Okay. So I'll let you guys set that up. I'll do this one too. And I'll give you just a couple of minutes. Okay, well, pause if you're not quite done yet. Let's do this one first. Probability, you draw a king and then an ace. So first we go with the probability of king. There are 4 kings in the 52 cards. Now we've chosen one card out of the deck, so there are 51 cards left, and there are 4 aces. So that's going to give us 0.006. Okay, so please be super careful. When you do this, you're going to move that decimal place 2 spots. That means that there is a 0.6% chance of king, then ace. Okay. Looking at the next one here, it tells us you draw a king, then an ace, then a 3. So we'll start off with our king, 4 out of 52. Then our ace is out of 51. And then our 3, that's out of 50. When we do that math, it gives us 4.8 e to the -4. Now, I think we've seen a number like this in this class, but let me remind you what that means. That means that this decimal right here moves 4 places in the negative direction. Negative direction is to the left, right? If we're thinking about a number line, that's the negative direction. So that number right there is actually 0.00048. Now you probably have to write it like that so you can then get the correct percentage. So when I move that decimal place over 2 spots, it goes right there. And so we wind up with 0.048% chance of king, ace, then 3. Okay, and finally, I like this one, the 4 hearts in a row. This is a good example. So how many hearts are there? There are 13 hearts. So we start off with 13 out of 52. Then we're left with 51 cards, and we're pulling another heart. Well, we've already taken one of the 13, so there's just 12 of 51 hearts. And then again, now we're left with 50 cards, and there aren't 12 hearts left. There's only 11 hearts left. And then finally, we're drawing from a pool of 49 cards, and there's only 10 possible hearts left. Do that. We get 0.0026. Moving that decimal place to here, so it's 0.26% chance of 4 hearts. Okay, let's drive that home with one more example. A math class consists of 25 students, 14 are female and 11 are male. 3 students are chosen at random to participate in a probability experiment. Compute the probability that a male is selected, then 2 females. So let's just stop right there. A male is selected, then 2 females. And we know that this is the probability of something, and it goes kind of in this order to has happened, is going to happen. Okay, so this is going to be the probability of a male is selected, then 2 females. So I'm going to say a female given another female given a male. I don't know why I was going to write a G for girl. Female, female, and girl. That was one thing. Male. Okay, and remember that it reads this way. Male first, and then 2 females. All right. So let's work this out. The probability of getting a male is going to be 11 out of the 25 students. Now, of the remaining 24 students, how many are female? 14. Of the remaining 23 students, how many are female? 13. It's going to give us 0.15. Which is 15% chance that we pick male, female, female. Okay, let's look at the next one. Let's see if you can't set this one up. Give about 5 or 10 more seconds. Yes, it's just the opposite. It is a female is selected, then 2 males. So we have a male given, we chose a male given we already had a female. So we'll do this guy here. So we have 14 over the 25. 24 remaining. how many males are available? 11. The 23 remaining, how many males are available? 10. Give us 0.112. Gives us 11.2% chance that we pick female, male. And finally, 3 males are selected. So that would be the probability that we chose a male, given we chose a male, given we already chose a male. So let's see what that's going to look like. Probability of choosing a male is 11 out of 25, leaving us 24 to choose. 10 males left, leaving us 23 left to choose, and 9 males left. So 0.072. So finally we have 7.2% chance that we pick 3 males. Okay, I'm going to take a quick break. Before I do, I'll be back in a second, but before I do, you two take yourself a little break. What we're fixing to get into is often very confusing. So, but it will be on your exam. It is usually the final exam's bonus question. So, this is not undoable, but it's helpful if we're all clear-minded when we do it. So I'm going to take a little quick break, and then I'll come back and we'll finish up this recording. Okay? All right.